Example 1. You push on mass 1. Mass 1 is up against mass 2, so it pushes on mass 2. And the result of your push is that the whole system of connected objects accelerates. We'll assume in this problem that there's no friction. We'll do some friction examples later. So in the procedure I just talked about in the previous video, what we need to do is analyze each of these two objects separately. So I'm going to draw a free body diagram for mass 1, first of all. We'll just use that standard horizontal, vertical coordinate system. Place mass 1 at the center. Mass 1 is experiencing several forces. It's experiencing that push. I'll label that the force from U on mass 1, Y for U pushing on mass 1. It's experiencing gravity force, so there's the gravity force of the Earth on mass 1, WE1. There's the normal force of the ground on mass 1, and there's one more force. It is the normal force between mass 1 and mass 2. They're touching, they're applying forces on one another. Mass 1 is applying a force on mass 2, but we don't include that in the free body diagram. We only include the forces on mass 1. By Newton's third law, that means mass 2 is applying a force of equal magnitude in opposite direction on mass 1. So that's considered a normal force as well. So there's another normal force of mass 2 on mass 1, pointing to the left. Now let's write down Newton's second law. In the y direction, we can kind of ignore it for this problem because there's no friction. And there's no acceleration in the y direction, so it's not very interesting. You'll just find that the normal force equals the gravity force. But in x, we need to do that. So the sum of the forces on mass 1 and x equals mass 1 times A1. I'm being careful to label the mass with a subscript and label its acceleration with a subscript. So I'm putting a 1 for mass 1. In the x direction, there are two forces. There's the push from U on mass 1, that's positive. And there's the normal force of mass 2 pushing on mass 1, that's going to the left, so that's negative. Now at this point, we're kind of stuck because we have one equation, but there's two unknowns in it. We don't know the acceleration yet. We also don't know how big that normal force is. So we can't really solve this. So let's just leave it for now, look at mass 2, and then figure out some connection between the equations we get. For mass 2, we'll use our standard horizontal vertical coordinate system. Place mass 2 at the center of that coordinate system. Mass 2 is experiencing gravity. There's the gravity force of the Earth pulling down on mass 2. It's experiencing a normal force from the ground. So there's normal force, the ground on mass 2. Again, that y direction is not very interesting because there's no friction in this problem. It's not accelerating in y. The x direction is where the action is. And first thing, or really the only thing to notice, is that the force in the x direction is that normal force of mass 1 pushing on mass 2. So just to be extra clear, this force on mass 2 is not from you. It's not the push, because you are not directly touching mass 2. What's directly touching it is mass 1. And those are two objects in direct contact. There's a normal force between them. So here is normal force of mass 1 pushing on mass 2. So the sum of the forces on object 2 in the x direction is m2 a2x, and there's only one of them. It's just this n1 2. Now once again, it seems like we're stuck because we don't know this n1 2 value, we don't know that a2 value. So now what we'll do is we'll use some common sense. From Newton's third law, we know that n21 equals n12. The magnitudes of those two vectors are equal. They point in opposite directions, as we indicated in the free body diagrams, but the magnitudes, with no vector signs, are equal. So we might as well just rename those both n, with no subscripts. Also, we know from common sense that the acceleration of each of these objects must have the same value. In other words, a1x must be the same thing as a2x. So we might as well just call that a. Those two accelerations are the same because the masses are connected and they're moving together. So with these substitutions, let's rewrite our two earlier equations. So we can rewrite this one as that pushing force from u minus n, the normal force between those two objects, equals m1 a. And this one can be rewritten as n equals m2 a. So now we have a little system of equations . And you can use your algebra skills to solve this system of equations. Now, in algebra class, you'll learn several ways to do this. I'm going to do it by substitution. So I'll substitute this value for n in the bottom equation into the top equation. Now a few steps of algebra and we'll be done. And here's our solution. After all that work, the solution is pretty simple. All it's saying is that the acceleration of each of these objects equals that push divided by the total mass of the system. In fact, you maybe could have guessed that at the very beginning of the problem without doing all this work. It makes sense that if you push an M1, it's kind of like there's just one big box of mass M1 plus M2. So it's sensible that its acceleration would just be force divided by total mass.